we are trying to get a feel of constraint satisfaction problems, and we were looking at the 6 queens problem, and we got a feel of the fact that the number of possibilities are so many, and somehow we have to sift through all of them and come up with the solution. And what does the solution look like? The solution basically has one edge between two variables. So, in this solution, you can see that queen A is placed on row 2, as you can see here. Queen B is placed on row 4, as you can see here, and so on and so forth. Queen C is played on row 6, and all these choices are a subset, all the edges that we have are a subset of the matching diagram. All these combinations are allowed. Of course, we did all this work in advance by stating the combinations which are allowed. It is just that we now want to sift through the fog. So, when we stated the CSP itself, we said that okay, yes, it can be solved provided these are the constraints that you satisfy, that A and B can be in these combinations and so on and so forth. Actually extracting a solution is a task of, in some sense, sifting, clearing that fog and arriving at a solution. Another interesting problem which has been posed as constraint satisfaction problem is the problem of interpreting line drawings, essentially, and it came from the field of early work on computer vision. I think this work was from MIT. There are 3 people involved in the story that we are looking at. The first was Guzman, who made the first attempt as to saying that okay, if you give me a line drawing. So, remember that it is assumed that you have taken a photo of some scene. Let us say it is some still life scene, and it is made up of only objects which are made up of straight lines. Then can you separate out one object from the other and things like that. So, he started with his work on interpreting line drawings, and that was part of his PhD work. Then it was not like making too much progress, and then along came Huffman. Huffman you may be familiar with if you have studied Huffman codes, the same Huffman. He was a mathematician, and he was trying to formulate the problem in a well defined way, which is what we will look at now. And eventually came David Waltz, who gave an algorithm, an efficient algorithm for solving the line drawing problem, which is also sometimes called as Huffman-Kloh labeling, by an efficient constraint satisfaction algorithm, essentially. So, let us look at what Huffman was saying. We will come back to Waltz in a later class. So, Huffman said that you want to work with trihedral objects only. Guzman was less restrictive over this when Huffman realized that these problems are not so easy, and you restrict the class of objects that you will look at, and he stated that you should look at trihedral objects only. What are trihedral objects? Objects in which 3 faces, 3 plane faces, they meet at every vertex, or alternatively you can say that 3 edges meet at every vertex. So, exactly 3, not less, not more. Such objects are called trihedral objects, and you can see that the figure that I have drawn in green satisfies these conditions, and the figure that I have drawn in red does not, essentially. Why? First of all, it should be planes, it cannot be curved edges, and secondly, we had this constraint of 3. So, if you imagine the top surface of the object on the right, and particularly if you focus on the fact that there is a vertex which has only 2 edges coming into to meet together, you can see that the top surface is not a plane, it has some kind of a weird curved surface in which an edge cannot be seen. If I had drawn an edge from here to, let me see, if there was an additional edge from here to here, and this was like this and this was like this, then it would become trihedral. But as given to us, this thing is not a trihedral object essentially. So, Huffman said restrict yourself to trihedral objects. Then he said that, and we will see this shortly, that there are only 18 types of junctions that can be possible. So, by junctions and vertices we will use the terms interchangeably, edges and lines we will use the term interchangeably. Huffman further said that the figure must be such that there are no shadows and there are no cracks. Not only that, they must be all viewed from a normal perspective. What is a normal perspective? A normal perspective is one where if you shift it slightly, the figure should not change drastically. So, the figure on the top right, as you can see, is the same as the figure on the left, but the diagram, the line diagram, is not normal perspective, because it is seeing it from a frontal view, and if you were to shift your point of view a little bit to the left or a little bit to the right or even a little bit above or below, you would see a totally different line drawing. So, he said, Huffman said, do not work with such figures, they must be in what he called as normal position essentially, and this figure on the left here in green satisfies this property. Now, he had said that there are only 18 types of junctions here. So, let us look at that next. And before we do that, we should specify that Huffman's goal was not to write a program to solve the problem. Huffman's goal was to analyze the problem from the mathematician's point of view. And he wanted to ask the question whether a line drawing represented a valid trihedral object or not. So, as you can see with this figure, the answer should be no, whereas on the figure in the green the answer should be yes. Now, if you want to look at this history of this problem, there is a nice video by Patrick Henry Winston, who was one of the founders of AI, and in the 70s and 80s he had written a book which was very popular. Unfortunately, he passed away, was it last year or the year before last? And there is a video available from the MIT free courseware. I have given you a link here. If you can access the link, it should be accessible through the slide, I hope. But I have also given you the name of the video. So, if you go to YouTube and look for this title, Constraints Interpreting Line Drawings, you will get this video and you will get a history of this problem, starting with Guzman and going on to Huffman and to Walls essentially. We will come back to Walls later. So, let us focus on this problem of how to label these line drawings. And what do we mean by label? We want to characterize the edges in a particular way. So, what Huffman said, that there are only 4 types of edges and there are only 18 types of vertices. If your object is trihedral, there are no cracks, there are no shadows and things like that, then we can work with that. So, there are 4 kinds of edges. Let us start with that. These are 2 of them are called arrows. They are similar except that the arrows are pointing in the different direction on the same line. The interpretation of an arrow is that it shows an object in which there is material on the right as you go along the direction of the arrow. So, in the left line you can see that the material would be on this side essentially, and on the right hand side you can see the material will be on the other side essentially. What do we mean by that? So, for example, this could be an object which looks like this, something like that, and you are seeing an edge which kind of defines the boundary of the object, and it defines it in such a way that the material is on the right hand side. So, these 2 kinds of arrows are called, these 2 kinds of edges are called arrows, and basically the direction changes where the material is. Then we have a convex edge uh, which tells you that the two planes which are defining that edge, they form a convex body. So, this particular thing could be labeled as a convex edge here, and we have correspondingly a concave edge. So, here is an example of the same object that we saw in the last slide and the label that we are seeking essentially. So, our task is to arrive at this labeling for each edge, give it a value, and the value is from this domain of 4 labels telling you what kind of an edge it is essentially. The typical algorithm would say that traverse the identify the objects, isolate it in some way, identify the boundaries, label the boundaries with the arrows, and then label the other edges essentially. Now, if you are going to do brute force search, then you can see that every edge can be labeled in 4 ways essentially, and look at the number of edges in the diagram and then look at the number of combinations. You know, this fog that we were talking about when we were talking about the 6 queen problems, you can visualize something similar here as well. So, that is a huge number essentially. What Huffman observed, that you do not have to try all those combinations, that only certain combinations are allowed for vertices essentially. So, that is what he said, that there are 18 kinds of vertices. Before we look at those 18 kind of vertices, let us look at another example here to say that we can do valid labeling, but it can still have ambiguity about this. So, if you look at this diagram and try to visualize it based on the labeling that has been done, then you can see that the inner part is kind of hollow essentially, that the outer surface is, that this is the surface which is for example facing you, but those inner vertex is inside a hollow. It is like looking at the corner of a room from inside. So, if you are sitting in a room and you look at a corner, then this is the kind of edge that this is the kind of vertex that we will see. Each of those 3 edges will be negative in nature, which means they are concave, and it is like sitting inside a room and seeing a cross section of the room essentially. But a perfectly valid labeling would also be like this, in which the inner 3 edges are labeled with pluses and there is change in the other edges as well. So, now you can see that the inner part can be seen as a cube. So, this is one face of a cube, this is another face of a cube, and this is the top face of a cube, and you can imagine this cube is in the corner of a room. So, it is against a wall and you can't distinguish whether it is one object or 2 objects. So, you have a negative edge there essentially. So, you could have ambiguity even for labeling these things. So, coming back to the question of 18 types of variables, 18 types of vertices, what Huffman observed was that there are, first of all, there are 4 types of vertices. We look at each of them one by one. One is called the Y joint or the fork, because the 3 edges, they look, as you see on the top, they look like a fork, and the 3 edges are labeled A, B and C, and they can be labeled in only these ways essentially. So, either all 3 can be plus as seen here, or all 3 can be minus. That is the example that we just saw in the last slide, either a cube or the corner of a room from inside. But also if you are seeing some edges, some boundaries, arrows, then you have 3 combinations, but only these are allowed, and no other combinations are allowed. Remember, we are talking about trihedral objects, which are just a subclass of objects essentially. So, instead of 64 possible ways of labeling A, B and C, we have brought them down to 5 essentially. And as we will see later when we look at Wald's algorithm, uh, even these combinations we do not have to try by brute force essentially. Then there is a W joint or an arrow joint, because it looks like an arrow or it looks like a W, as you can see here. And it turns out that it can be labeled only in 3 ways essentially. I would urge you to draw objects and try and see that no other way is possible essentially. So, you can see a W joint here, for example, it has a label of minus plus minus, which is this one here. You can see another W joint here, which has a label of arrow arrow plus. So, arrow arrow plus essentially, and the third one can be plus minus plus, which is not there in this figure, but in the other figure that we drew, it should be there essentially. Then there are the T joints, that from certain angles, some objects will have these kind of edges essentially. So, these are the in my diagram there are 6 of these, but in some, in fact, in Huffman's own work there were only 4 of them, because he felt that 2 of them were kind of same essentially. And then we have the L joints. So, for example, here is an L joint and here is an L joint and here is an L joint and here is an L joint. All these are L joints, and you can label them in one of these 6 possible ways. So, in this diagram there are 20 ways, but in Huffman's own formulation there were these 4 that I have mentioned were collapsed into 2 essentially. So, how does one go about doing this? So, as I was saying that the property you want to exploit or the constraints that you want to exploit are that an edge or a line cannot change its nature from one vertex to another. So, if you have an edge connecting these 2 vertices, you can only label it in one way at both the vertices essentially. And this is what this diagram is showing, that this vertex V1 and this vertex V2, these are the allowed vertices for V1, which is a W type of vertex here, and these are the allowed vertices for V2, which is a Y type of a vertex here. But it says that the middle one in the V1, which is this one or this one or this one, must correspond to one of them in the this thing. So, you can see immediately that for this vertex these cannot be possible combinations. So, this is a basic feel of this idea of propagation that we are slowly working through, that only certain combinations are allowed essentially. Likewise, between V2 and V3 we can see that only certain combinations are allowed. So, here is a even simpler block. It looks like a slice of cheese as often depicted in diagrams. It has got these 6 vertices. It is basically a triangular block. It has a 6 vertices and it has got 2 of them are L vertices. As you can see, this is L and V2 is L. One of them is a Y vertex, which is the center one, and the other 3 are W vertices. And these are the names of those 3 edges that we are talking about, and of course, we have to find values for them. Remember, our task is to find labels for edges. So, in this case the edges are A, B, C, and we have just labeled them 1, 2, 3, so that we understand that when we draw a full diagram for this, what are we talking about here essentially. So, when we start, when we pose the CSP, this is what we pose as a constraint satisfaction problem. These 6 vertices, the allowed values as specified by Huffman for those 6 vertices. So, for example, V5 has 3, V1 also has 3. So, these W vertices have only 3 possibilities. Okay. So, these are the 3 possibilities, and they are all listed in all the W vertices. There are 3 of them, as you can see, V5, V1 and V6. What this notation which I have used says that if you look at the first element of V5, which is either this or this or this, it must be equal to the third element of V6, which is either this or this or this. Why? Because they are joined by an edge together and the label must be the same essentially. That is what the constraint is saying, that is what the partial description of the labeling is saying, that this is how you, this is a combination of things you allowed for V5 and V6 essentially. So, you have to choose something where both the sides are the same essentially. In this example, all 3 values are allowed. So, the possibilities still remain, but if you work through this whole thing, you will see that you can, if I may use the phrase, cut through the fog, but we will come back to that when we look at the Waltz algorithm. I want to take one more example, which is a very popular example. It is a big application of using constraints, and that is the task of model based diagnosis, and we will do that after a short break in the next video. So, see you in a while.